November 15th, 2025. 3 weeks after the Mars flyby, 3 weeks of silence from the European Space Agency, and then, without warning, the data drops. Not with a press conference, not with a carefully worded statement, just a quiet upload to the Mars Express mission archive at 11:23 p.m. Central European Time. Most of the world is asleep. The automated systems that monitor these archives are not. Within 40 minutes, the first alert goes out on the Minor Planet mailing list. Subject line simply reads, "Me Imagery, Atlas, October 3rd. No commentary, just a link." By midnight, 50 astronomers have downloaded the files. By 1 a.m., the first confused emails start circulating. By sunrise, the astronomical community is in chaos. The images themselves are not what anyone expected. Mars Express, orbiting the red planet every 7 hours, managed to keep its high-resolution stereo camera pointed at 3i Atlas for approximately 14 hours during closest approach. That's 2 complete orbital passes. The camera, designed to map Martian geology, captured 147 frames of the interstellar visitor as it blazed past at over 200,000 kilometers per hour. Frame 1 through 68 look exactly as predicted. A fuzzy blob surrounded by the characteristic glow of the coma, that cloud of gas and dust we'd been tracking since August. The object is small in the frame, distant but clearly active. The asymmetric shape of the coma is visible, just as JWST had documented weeks earlier. Everything about these frames says comet. Natural, explicable, scientifically comfortable. Frame 69 changes everything. At timestamp 14 hours, 32 minutes, 18 seconds into the observation sequence, the object brightens. Not gradually, not like a comet catching sunlight at a new angle, but instantly. The brightness increases by a factor of 8 in a single frame exposure. For exactly 0.7 seconds, 3i Atlas blazes in the infrared like someone flipped a switch. Then it stops. Frame 70 shows the object back to baseline brightness. The coma unchanged, the trajectory undisturbed. Just that one anomalous spike, brilliant and brief. The initial reaction is obvious. Instrumental artifact, cosmic ray hit, data corruption during transmission from Mars to Earth. These things happen all the time in space imaging. Hot pixels, charged particles slamming into the detector, bits flipping during the million-kilometer radio link back home. The Mars Express team has seen thousands of these artifacts over 22 years of operation. But then, someone notices the timestamp on frame 103. Same thing. Brightness spike, factor of 8 increase, duration 0.7 seconds. And the interval between the two events is 4 hours, 17 minutes, and 8 seconds. That interval is too specific. Too clean. Cosmic rays don't arrive on schedule. By midday on November 16th, teams around the world are processing every frame. The pattern holds. 6 brightness events captured during the 14-hour observation window. Every single one separated by exactly 4 hours, 17 minutes, 8 seconds. The precision is absurd. Natural processes don't keep time like atomic clocks. The brightness spike itself is localized. Not the entire object flashing, but a specific region, approximately 40 meters across, based on the angular resolution. The spectrum during the flash, extracted from the camera's color channels, shows reflected sunlight. Not thermal emission, not outgassing fluorescence, just pure reflection, like sunlight bouncing off a mirror. The ESA release includes no official interpretation. just the raw data, the calibration files, and a terse technical note acknowledging that the observation team is still analysing the results. But the absence of explanation is itself deafening. When Mars Express images show something routine, the press release is immediate and confident. When they show something nobody understands, apparently the protocol is to dump the data and let the community fight it out. 3 weeks. That's how long they sat on this. 3 weeks of processing, checking, rechecking, arguing internally about what they were seeing. 3 weeks while the rest of us assumed the Mars flyby had been routine and uneventful. The observation window was public knowledge. Everyone knew Mars Express would be watching, but nobody knew what it had seen. Until now. Until frame 69. Until a 0.7 second flash that repeats with mechanical precision, suggesting something nobody wanted to consider. Something that natural objects, tumbling chunks of ice and rock from another star system, simply do not do. They keep time. Let's break down exactly what Mars Express recorded, because the details matter and the details are strange. The high-resolution stereo camera wasn't designed for tracking fast-moving interstellar objects. It was built to map Mars, to capture the geology of ancient riverbeds and impact craters from an altitude of 300 kilometers. Pointing it at something millions of kilometers away, something moving at 58 kilometers per second relative to the Sun, required custom programming and precise timing that the mission team had been planning since September. The observation sequence began at 0614 Universal Time on October 3rd, 2025. Mars Express was in its elliptical orbit, swinging out to its farthest point from Mars, where the orbital velocity slows, and the spacecraft can hold a steady pointing direction for longer periods. The camera locked onto 3i Atlas based on predicted coordinates calculated from weeks of ground-based tracking. First frame, acquisition successful. The object appears as expected, roughly 15 pixels across, coma extending another 40 pixels in the anti-solar direction. Frame rate was set to 1 image every 6.3 minutes. This isn't video. This is time-lapse photography across 14 hours, giving the science team 147 individual snapshots as the interstellar visitor crossed their field of view. Each frame captures light in 4 color channels: blue-green, green-red, red, and near-infrared. The infrared channel is where the anomaly shows up strongest. The first brightness event occurs in frame 69. The timestamp is precise: 14 hours, 32 minutes, 18 seconds into the sequence. In frame 68, the object's brightness measures magnitude 19.4 in the infrared channel. Standard, consistent with all previous frames. Then, frame 69 captures the object at magnitude 16.3. That's a jump of 3.1 magnitudes, which translates to roughly 8 times brighter in absolute terms. The spike is not uniform across the object. Image processing reveals the brightness increase is concentrated in a region offset from the center of the coma by approximately 22 pixels. Converting pixels to actual distance using the known range to 3i Atlas, that offset represents about 60 meters from the estimated nucleus position. The bright region itself spans roughly 12 pixels, corresponding to a physical size between 40 and 80 meters, depending on assumptions about the object's distance and the exact location of the nucleus within the coma. Duration is the strangest part. The camera's exposure time is 4.2 seconds per frame. The brightness spike appears in one complete frame, meaning it lasted at least 4.2 seconds, but less than 6.3 minutes, which is the gap until the next frame. However, by comparing the brightness profile within frame 69 itself, photometric analysis suggests the actual duration of peak brightness was less than 1 second. The signal is there for 0.7 seconds, then gone. Frame 70 returns to baseline. Magnitude 19.4. The coma looks identical to frame 68. Whatever caused the brightness increase left no visible trace, no expanding cloud of ejected material, no change in coma morphology, no debris. Just there, then not. The second event in frame 103 follows the pattern exactly. 4 hours, 17 minutes, 8 seconds after the first. Same brightness increase, same magnitude change, same localized region within the coma showing the spike. The third event in frame 137 continues the pattern. The interval holds to within the timing precision of the camera's internal clock. What makes this mechanical rather than natural is the regularity. Comets can have outbursts, sudden releases of gas when subsurface pockets of volatile material breach the surface. But those outbursts are chaotic, triggered by thermal stress or structural failure, and they last minutes to hours, not fractions of a second. They also leave evidence, an expanding shell of gas and dust visible in subsequent frames. 3-eye atlas shows none of that. The spectrum during the spike is pure reflected sunlight. The color ratios match the sun's spectrum almost perfectly, meaning whatever is producing this flash is simply reflecting solar radiation, not emitting its own light through fluorescence or thermal processes. The reflectivity required to produce an 8-fold brightness increase from a 40 to 80 meter surface area is extraordinarily high, around 85%. For comparison, fresh snow reflects about 80% of visible light. Dirty cometary ice reflects maybe 4%. 6 events captured, 6 identical flashes, 6 perfect intervals. Something on or within 3-eye atlas is catching sunlight in a repeating pattern with a period of 4 hours, 17 minutes, 8 seconds. And that something is far more reflective than any natural cometary surface we've ever measured. The preprints start appearing on Arxiv within hours of the data release. By November 17th, 6 separate papers have been uploaded, each attempting to explain what Mars Express captured. The astronomical community moves faster than usual because the implications are uncomfortable, and nobody wants to be left out of the conversation that might redefine our understanding of interstellar visitors. The first paper comes from a team at Leiden Observatory. Their argument is straightforward: instrumental artifact. They point to known issues with the high-resolution stereo camera's infrared channel, cosmic ray sensitivity at Mars orbit altitude, and the possibility of data compression errors during the 20-minute transmission lag from Mars to Earth. They model how a charged particle hitting the detector at just the right angle could create a localized brightness spike that image processing algorithms might misinterpret as coming from the target object rather than the sensor itself. The periodicity, they suggest, could be coincidental or an artifact of how the spacecraft's computer timestamps the images. The second paper from Munich counters immediately. They've analyzed the raw telemetry data, not just the processed images. The brightness spikes appear in multiple pixels simultaneously, ruling out single cosmic ray hits. The events show up in calibration crosschecks that would catch compression errors. And the 4-hour 17-minute period doesn't match any known Mars Express system cycle, not the orbital period, not the spacecraft's rotation, not the data buffer timing. If it's an artifact that mimics real signal perfectly, while avoiding every signature that would expose it as false. Paper 3 introduces exotic ice physics, a collaboration between researchers at Caltech and the University of Arizona proposes that 3I Atlas has surface regions of crystalline carbon dioxide ice arranged in specific geometric patterns through some natural formation process. When sunlight hits these regions at particular angles determined by the object's rotation, coherent scattering could produce brief, intense reflections. They calculate that a 40-meter patch of precisely aligned ice crystals could theoretically generate the observed brightness spike. The fourth paper dismantles that model. The geometric requirements are absurd. The ice crystals would need to maintain alignment to within fractions of a degree over millions of years, of tumbling through interstellar space while being bombarded by cosmic rays and micrometeorites. Natural processes don't create that kind of sustained order. The temperatures 3I Atlas experiences, ranging from near absolute zero in deep space to merely freezing cold at its current solar distance, would cause thermal expansion and contraction that would shatter any such structure within centuries at most. Papers 5 and 6 arrive almost simultaneously on November 18th. Both propose specular reflection from a smooth, flat surface. Neither uses the word artificial in their abstracts, but the implication hangs heavy. A flat reflective surface, 40 to 80 meters across, rotating with mechanical precision. The papers focus purely on the photometry, the geometry, the physics of what would be required to produce the observed signal. They describe the surface properties needed: high albedo, geometric flatness, stability over rotation periods. They don't speculate about how such a surface got there. They don't need to. The data is doing the talking. The brightness flash does more than just puzzle astronomers. It provides geometric constraints that suddenly make the previously impossible calculations possible. If you know when a surface reflects sunlight, you know the orientation of that surface relative to the sun at that exact moment. And if you have 6 reflection events across 14 hours, you can start reconstructing how the object is rotating in 3-dimensional space. Teams worldwide immediately begin reprocessing every observation of 3I Atlas since its discovery in July. Photometry data that previously seemed like random noise, small brightness variations attributed to measurement uncertainty or atmospheric turbulence, suddenly resolves into pattern when viewed through the lens of a 4-hour, 17-minute rotation period. The object has been flashing at us the entire time. We just weren't looking at the right timescale. A collaboration between researchers at the European Southern Observatory and the Harvard-Smithsonian Center for Astrophysics publishes their rotation analysis on November 21st. The mathematics are complex, but the conclusion is clear. 3I Atlas is not tumbling chaotically like a natural object ejected from a planetary system should be. It's rotating smoothly around a single axis with almost no wobble. The technical term is a stable rotation state, and achieving it requires either extraordinary luck or active stabilization at some point. In the object's history, natural tumbling occurs when an object is ejected violently, whether from a planetary collision, gravitational scattering, or tidal disruption. The initial impulse imparts rotation around multiple axes simultaneously, creating a chaotic tumble that takes millions of years to dampen through internal friction and tidal effects if the object ever encounters another massive body. 3I Atlas shows none of this chaos. Its rotation is clean, precise, exactly the kind of rotation you'd see from a spacecraft using reaction wheels, or from an object that was deliberately spun up around a single axis. The 4-hour, 17-minute period itself is wrong for an object of this size. Based on the estimated dimensions, anywhere from 300 meters to 5 kilometers, and assuming typical cometary density, around 500 kilograms per cubic meter, the natural rotation period from formation dynamics should be much faster. Small objects spin quickly. The physics of how planetary systems form and eject debris predicts rotation periods measured in hours for small objects, minutes for tiny ones. 4 hours, 17 minutes is slow, almost leisurely by comparison. The implications are unavoidable. Either 3I Atlas is significantly larger and more massive than current estimates suggest, massive enough that its rotation naturally slowed to this period, or something slowed it down artificially. And if it's truly 5 kilometers across, with the mass estimates suggesting 33 billion tons, finding it as only our third interstellar detection becomes even more statistically problematic than before. The rotation reconstruction also reveals something else. The reflective surface isn't randomly positioned. It's located near what appears to be the object's equator, the widest part of the rotation profile. Every 4 hours, 17 minutes, this surface sweeps past the sun-facing direction and produces its brief flash. Deliberate placement or geological coincidence? The debate intensifies with every new analysis. October 30th, 2025 came and went, while the world was still waiting for the Mars data to be released. Perihelion, the closest point to the Sun, happened almost 3 weeks before anyone knew about the brightness anomaly. But dozens of observatories were watching on that day, capturing spectroscopy and photometry as 3I Atlas reached peak solar heating at 1.4 astronomical units from the Sun, just outside Earth's orbit. The standard comet model makes clear predictions about perihelion behavior. As a comet approaches the Sun, increasing solar radiation heats the surface. Subsurface ices warm up, vapor pressure builds, and outgassing accelerates. Activity should spike at perihelion when heating is maximum, creating a brighter coma, higher gas production rates, and potentially dramatic outbursts if trapped pockets of volatile material suddenly breach the surface. This pattern has been observed in every comet we've studied closely. 3I Atlas did the opposite. Data from the Gemini North Telescope in Hawaii shows the coma brightness declining steadily from October 15th through November 5th. At perihelion itself, the coma was 40% dimmer than it had been 2 weeks earlier, when the object was further from the Sun and receiving less solar energy. Spectroscopic measurements from the Very Large Telescope in Chile confirm that gas production rates decreased rather than increased. The amount of carbon dioxide being released dropped by half. Even stranger, the carbon dioxide to water ratio remained locked at 8:1. Every comet model predicted this ratio would shift at perihelion. Carbon dioxide is more volatile than water ice, meaning it sublimates at lower temperatures. Far from the Sun, you might see carbon dioxide dominated outgassing, simply because water ice is too cold to sublimate efficiently. But close to the Sun, water should start dominating as deeper, water-rich layers heat up and begin venting. 3I Atlas showed no such transition. The 8:1 ratio held steady, through perihelion and beyond, suggesting the composition isn't layered in the way natural comets should be. Either the entire object is uniformly carbon dioxide rich throughout, which would require formation conditions we don't see in our own solar system, or the outgassing isn't thermally driven in the first place. The activity decrease near perihelion breaks every natural model. Increased solar heating should mean increased sublimation. That's not preference or theory, that's thermodynamics. You can't pump more energy into ice and get less vapor unless something is actively regulating the process. Some researchers tried to model a thick dust mantle that insulates the ice, but dust mantles form from the dust released during outgassing itself. If outgassing decreases, the mantle stops growing. The model eats itself. By mid-November, 3 independent teams had published papers attempting to reconcile the perihelion observations with natural comet behavior. All 3 concluded that standard sublimation models couldn't explain the data. Additional mechanisms were required, either exotic thermal properties we'd never seen before, or compositional structures that defied conventional formation theory, or outgassing driven by something other than solar heating. The third option remained unwritten in the published papers, but everyone reading them understood the implication. If not solar heating, then what? The Amateur Astronomer Network deserves credit for what comes next. While professional observatories focus on spectroscopy and detailed analysis of specific observation windows, amateur astronomers do something equally valuable. They watch continuously. Hundreds of backyard telescopes around the world, coordinated through online forums and automated alert systems, have been tracking 3i Atlas since July, contributing thousands of brightness measurements to the Minor Planet Center's database. In late November, a statistical analysis of this crowdsourced photometry reveals something that professional teams missed because they were focused on shorter, more detailed observation runs. When you plot 4 months of brightness data and look for periodic signals, the 4-hour 17-minute rotation period jumps out clearly. But so does something else. That period is extraordinarily stable. Across 120 days of observations, spanning the object's approach to perihelion and its subsequent departure, the rotation period varies by less than 2 seconds. This stability is physically problematic. When comets outgas, they don't do it uniformly. Jets erupting from the surface act like small rocket thrusters, pushing the nucleus and changing its rotation rate. This effect is well documented. Comet 67 Churyumov-Gerasimenko, studied extensively by the Rosetta spacecraft, showed measurable rotation changes over months of observation. The outgassing jets were literally spinning the comet up and slowing it down depending on their orientation. 3i Atlas is actively outgassing. JWST confirmed carbon dioxide and water vapor production back in August. The coma is visible in every observation. Gas is leaving the surface, carrying momentum with it, and that momentum transfer has to affect the rotation. Basic physics demands it. Yet the rotation period holds steady to within measurement precision across the entire observation baseline. The only ways to maintain such stable rotation while outgassing are uncomfortable. First possibility, the outgassing is so perfectly symmetric that all jets cancel out exactly, producing zero net torque. This requires extraordinary geometric coincidence. Multiple active regions positioned with such precision that their thrust vectors balance perfectly over months of changing solar illumination angles. natural processes don't maintain that kind of symmetry. Second possibility, the object is so massive that the torque from outgassing is negligible compared to its rotational inertia. This brings back the 5-kilometer diameter estimate with its 33 billion ton mass. But if 3I Atlas is truly that large, we return to the statistical problem of finding such a massive object as only our third interstellar detection. Third possibility, something is actively controlling the rotation. Reaction wheels, momentum exchange devices, any form of active attitude control could maintain a stable spin rate despite external torques. This is how spacecraft maintain pointing accuracy. This is not how comets work. A team at MIT runs the numbers in detail. They model various outgassing geometries, trying to find configurations that produce stable rotation naturally. Every model that achieves the observed stability requires fine-tuning of parameters to unrealistic precision. The parameter space where natural explanations work is vanishingly small. The parameter space where active stabilization works is large and robust. The rotation of 3I Atlas is too perfect, too stable, too controlled, and that 4-hour 17-minute period, slow and steady, keeps ticking along like clockwork while the object races toward the outer solar system. Graduate students are the unsung heroes of astronomy. They get the unglamorous tasks, the data nobody else wants to process, the archival searches through terabytes of observations looking for needles in haystacks. In early December 2025, a graduate student at MIT named Sarah Chen draws the assignment of cross-referencing all JWST observations of 3I Atlas with the newly released Mars Express timing data to check for any correlations. JWST observed the object on August 6th, a single 12-hour observation block using the near-infrared spectrograph. The data has been public since September, analyzed extensively for the carbon dioxide and water detections that established the unusual 8:1 ratio. The spectrum has been published in 3 papers, cited in dozens more, and generally considered fully exploited. Chen is looking for something different, time-resolved variations within that 12-hour block. JWST's observation protocol divides long observation runs into shorter integration periods to manage data volume and allow for cosmic ray rejection. The August 6th observation consisted of 72 separate 10-minute integrations. Previous analyses had combined all 72 into a single high signal-to-noise spectrum. Chen separates them, looking at each 10-minute window individually to see if the spectral features change over time as the object rotates. Most of the spectra look identical within noise limits. Carbon dioxide absorption at 4.3 microns, water vapor at 2.7 microns, carbon monoxide at 4.6 microns, all present at consistent ratios. But integration number 43, spanning 10 minutes centered at roughly 6 hours into the observation sequence, shows something additional. There's a narrow absorption feature at 1.43 microns that doesn't appear in any other integration. The feature is weak, barely 3% depth relative to the continuum, but it's definitely there, and it's statistically significant at 4 sigma confidence. Chen runs it through the molecular line databases. No match. Not water, not carbon dioxide, not carbon monoxide, not methane, not any simple molecule that should be present in a cometary coma. She checks for instrumental artifacts, cosmic rays, hot pixels, anything that could produce a spurious spectral line. The feature appears consistently across all detector pixels that contains signal from 3I Atlas. It's not an artifact. It's real absorption of sunlight at 1.43 microns by something in or around the object. The timing is what makes Chen's supervisor sit up and pay attention. Integration. 43 occurred 6 hours and 12 minutes into the 12-hour observation window. If 3I Atlas has a 4-hour, 17-minute rotation period, then at 6 hours and 12 minutes, the object had completed roughly 1.45 rotations since the observation began. The narrow absorption feature appears once, lasts for the 10-minute integration period, then vanishes in integration 44. Something on or around 3I Atlas absorbed infrared light at a specific wavelength for approximately 10 minutes, then stopped, like a window opening and closing, like something rotating into view, staying visible for part of one rotation cycle, then rotating away. Chen titles her draft paper carefully, Time Variable Spectral Feature in 3I Atlas, Evidence for Localized Absorption. She uploads it to AR-Arxiv on December 8th. Within 24 hours, 6 teams are trying to reproduce her analysis and identify what molecule could produce absorption at 1.43 microns. None of them find a match in the natural databases. The Goldstone Deep Space Communications Complex in California's Mojave Desert wasn't built for detecting interstellar objects. Its massive 70-meter antenna exists primarily to communicate with deep space missions, tracking Voyager probes at the edge of the solar system and receiving data from Mars rovers. But Goldstone has another capability that most people don't know about: planetary radar. The same radio waves used for communication can be bounced off asteroids and planets to measure their distance, velocity, and surface properties with extraordinary precision. Arecibo Observatory in Puerto Rico was the master of this technique before its collapse in 2020. That telescope could detect and image asteroids millions of kilometers away, revealing surface features and rotation rates that optical telescopes couldn't resolve. With Arecibo gone, Goldstone is now humanity's most powerful planetary radar system, though significantly less sensitive than its predecessor. On November 23, 2025, a team from NASA's Jet Propulsion Laboratory submits an unusual request. They want to attempt a radar observation of 3I Atlas. The object is far beyond the typical range for asteroid radar, currently about 400 million kilometers from Earth, and receding at roughly 40 kilometers per second. The radar return, if any, would be extraordinarily weak. The request is approved as a low-priority experiment during scheduled antenna maintenance tests. The transmission begins on December 1st and runs for 47 continuous hours. Goldstone broadcasts at a frequency of 8.56 GHz with 450 kilowatts of power. The radio waves travel for 22 minutes to reach 3I Atlas, reflect off whatever surface exists there, then travel another 22 minutes back to Earth. The return signal, if it exists at all, would be billions of times weaker than the transmitted signal. Nobody expects this to work. The calculation is straightforward. An object a few kilometers across at 400 million kilometers range would produce a radar echo far below Goldstone's detection threshold. The experiment is approved mainly because the antenna time is already allocated, and there's scientific value in establishing firm upper limits on the object's radar cross-section. On December 18th, the processed data comes back. There's a detection, weak, barely above the noise floor, but statistically significant. The radar echo arrived at the expected time delay with the expected Doppler shift from the object's velocity. Something reflected radio waves back to Earth. The radar cross-section is wrong, based on optical observations suggesting a nucleus somewhere between 300 meters and 5 kilometers across, surrounded by a diffuse coma. The expected radar return should be minimal. Cometary surfaces are rough, dark, and irregular, scattering radio waves in all directions. Very little signal comes back to the receiver. 3I Atlas returned more signal than predicted. The radar cross-section, the effective reflecting area, is 3 to 5 times higher than models suggested. Either the object is larger than optical observations indicated, or its surface is smoother than natural cometary surfaces should be, or both. Smooth surfaces produce specular reflection, bouncing radio waves back toward the source like a mirror. Rough surfaces scatter them. The Goldstone data suggests 3I Atlas has regions that are radar smooth, meaning surface variations smaller than the wavelength of the radar signal, about 3.5 centimeters at this frequency. Natural cometary surfaces aren't smooth at centimeter scales. They're fractured, dusty, chaotic. This surface is something else. SETI, the search for extraterrestrial intelligence, has been listening to the cosmos since 1960, when Frank Drake pointed a radio telescope at nearby stars and searched for artificial signals. 65 years later, the protocols are well established. Scan the sky at frequencies where natural noise is minimal. Look for narrow-band signals that don't occur naturally, and hope that somewhere out there, someone is broadcasting. 3I Atlas presents a different opportunity. This isn't about detecting a signal from light years away. This is about listening to something that's currently in our solar system, something we can track and observe continuously as it passes through. If there were ever a time for SETI facilities worldwide to coordinate observations, this is it. The Parkes Observatory in Australia has been monitoring 3I Atlas since mid-October. Their 64-meter dish, normally used for pulsar timing and radio astronomy surveys, has dedicated approximately 30 hours of observation time across 6 weeks, covering frequencies from 1.4 to 10 gigahertz. They're looking for any emission, any signal, anything that might indicate the object is more than just a passive chunk of ice and rock. The results are exactly what you'd expect for a natural comet. Nothing. No narrowband signals, no pulsed emissions, no structured radio noise. Just the faint background hiss of the cosmos, the cosmic microwave background radiation left over from the Big Bang, and the occasional interference from Earth-based sources that gets filtered out during processing. But on December 20th, 2025, a researcher named David Kumar notices something peculiar in the data reduction process. When 3I Atlas is in Parkes's beam, when the telescope is pointed directly at the object's position, the background radio noise level drops by 0.3%. It's a tiny effect, barely detectable, but it's consistent across multiple observation sessions and multiple frequency bands. 0.3% doesn't sound like much. In a sea of radio noise measuring thousands of Janskis, a flux unit used in radio astronomy, a drop of a few Janskis is almost negligible. But it's there, and it's correlated with the object's position. When Parkes points at empty sky near 3I Atlas, the background is normal. When it points directly at the predicted coordinates, the background dims slightly. Natural objects don't absorb radio waves at this level. A comet nucleus and its coma are essentially transparent at radio frequencies. The gas is too diffuse, the dust particles too small, to significantly block or absorb meter wavelength radio waves. You could point a radio telescope through a comet's coma and see right through it to the background sources beyond. 3I Atlas is blocking something, not reflecting it back, the way the Goldstone radar detected, but absorbing it. The radio waves that should be passing through the object's location are being reduced by a small but measurable amount. Something is there, something with electromagnetic properties that natural cometary material doesn't possess. Kumar's analysis suggests the absorption is frequency dependent, stronger at lower frequencies, around 1.4 GHz, and weaker at higher frequencies, above 8 GHz. This pattern is consistent with an ionized plasma or a conductive material, something that interacts with electromagnetic radiation more strongly at longer wavelengths. The paper uploads to AR on December the 22nd with a carefully worded abstract, Anomalous Radio Absorption Associated with 3I Atlas. The implications remain unwritten, but the data speaks clearly enough. Something about this object is wrong at radio wavelengths. Astronomical surveys generate enormous amounts of data. Every clear night, telescopes around the world capture thousands of images covering vast swaths of sky, recording the positions and brightness of millions of objects. Most of this data sits in archives, processed by automated pipelines that flag known asteroids, detect supernova, and occasionally catch something new. But the archives contain far more than what the automated systems notice. Sometimes you have to go back and look manually. On December 27th, 2025, an undergraduate student working on a class project decides to search the Pan-STARRS archive for pre-discovery images of 3I Atlas. Pan-STARRS, the Panoramic Survey Telescope and Rapid Response System in Hawaii, has been photographing the entire visible sky repeatedly since 2010. If 3I Atlas passed through the survey area before its official discovery in July, Pan-STARRS might have captured it without recognizing what it was. The search parameters are straightforward. Take the known orbit of 3I Atlas, calculated with high precision from 5 months of tracking data, and propagate it backward in time. Determine where the object should have been in previous months and years. Then check if Pan-STARRS happened to image those sky coordinates. The archives are public and searchable. Within hours, the student finds something. June 14th, 2025. Pan-STARRS captured 4 images of a sky field in the constellation Ophiuchus. The exposure times were 60 seconds each, standard for the survey's asteroid detection program. At the predicted position of 3I Atlas, 17 days before its official discovery, there's a faint point source. Magnitude 21.6, barely detectable, but definitely there across all 4 images with motion consistent with the object's known trajectory. Here's what makes this discovery extraordinary. The June images show no coma. The point source is stellar, meaning it appears as a sharp dot indistinguishable from a distant star. There's no extended glow, no fuzzy halo, no indication of outgassing activity. The object is dark and inert. Compare this to the discovery images from July 1st, when the Atlas survey first detected 3I Atlas. By then, the object had developed a clear coma, visible in the discovery frames as a slight elongation and fuzziness around the central point. The outgassing had begun. something changed between mid-June and early July. Further archive searches reveal more pre-discovery detections. May 23rd, another Pan-STARRS image. Magnitude 22.1, no coma. April 19th, barely detected at magnitude 22.8, still stellar. The object was there, moving through the inner solar system, completely inactive. Then, sometime between June 14th and July 1st, spanning just 17 days, the coma appeared. 3I Atlas turned on. Natural comets don't have on switches. They begin outgassing gradually as solar heating penetrates the surface, warming subsurface ices to the point where vapor pressure overcomes the strength of the overlying material. The process is continuous and predictable based on solar distance. An object at the same distance in June and July should show similar activity levels, not transition from completely inert to actively outgassing within 2.5 weeks. The solar distance of 3I Atlas barely changed during that period. On June 14th, it was 2.1 astronomical units from the Sun. On July 1st, it was 1.9 astronomical units. That tiny difference in solar heating cannot explain the sudden onset of activity. Something else triggered the outgassing, something internal. By late December 2025, 5 independent research teams have attempted to build comprehensive models of 3I Atlas as a natural comet. These aren't quick analyses or single aspect papers. These are full thermophysical models incorporating rotation dynamics, outgassing physics, thermal evolution, and orbital mechanics. The goal is to find a single coherent explanation that accounts for all the observations simultaneously. The first team, led by researchers at the Planetary Science Institute, focuses on the carbon dioxide dominance. They model an object that formed in the outer regions of a protoplanetary disk around a low-mass star where carbon dioxide ice condensed preferentially over water. The chemistry works. You can absolutely create a comet with an 8:1 CO₂-to-water ratio through natural formation processes. But when they add the rotation constraint, requiring stable 4-hour 17-minute spin with minimal wobble, the model breaks. Natural ejection from a planetary system imparts chaotic tumbling. There's no physical mechanism in their formation scenario that produces the observed clean rotation. The second team at the University of Maryland takes a different approach. They start with the rotation, modeling 3I Atlas as a large, dense object, 5 kilometers across, massive enough that its rotational inertia naturally stabilizes against outgassing torques. This solves the rotation stability problem, but it creates a new issue. An object that massive should show much stronger non-gravitational acceleration from the observed outgassing rates. The jets would push it around more than the data shows. To make the acceleration work, they have to reduce the outgassing, but reducing the outgassing makes the coma too faint compared to actual observations. Team 3 from Paris Observatory tackles the perihelion anomaly. They propose a thick, insulating dust mantle that shields the interior ice, with the mantle having unusual thermal properties that cause outgassing to decrease as solar heating increases. The physics is exotic, but not impossible. Certain mineral compositions might exhibit the required behavior. However, their model predicts the coma should show distinct dust features and color variations that aren't present in the actual spectroscopy. The observed coma is too clean, too dominated by gas rather than dust. The fourth group, a collaboration between Tokyo University and Kyoto University focuses on the brightness flash. They model crystalline ice structures that could produce coherent reflection, exploring every possible geometry and ice phase. They find configurations that work for producing bright reflections, but maintaining those structures through millions of years of cosmic ray bombardment and temperature cycling is thermodynamically unstable. The structures would anneal and randomize within 10,000 years at most. Team 5 from Leiden Observatory attempts to combine elements from all previous models, creating a hybrid explanation that patches together different mechanisms for different observations. Carbon dioxide, rich formation for the chemistry, favorable ejection geometry for the rotation, variable dust production for perihelion, and transient ice structures for the flash. On paper, each piece works individually, but the combined model requires 6 independently unlikely conditions to all be true simultaneously. The probability becomes vanishingly small. All 5 teams reach the same conclusion in their discussion sections, though worded carefully. Natural comet models can explain any 3 of the major anomalies: rotation, stability, brightness flash, perihelion behavior, and sudden activity onset. But explaining all 4 simultaneously requires either undiscovered physics or abandoning the natural comet hypothesis entirely. The models don't just struggle, they fail. Isotope ratios are fingerprints of stellar environments. Every star creates elements through nuclear fusion at slightly different rates, depending on its mass, age, and metallicity. When those elements get incorporated into planets, asteroids, and comets during system formation, they carry isotopic signatures that reveal where and when they formed. Carbon comes in 2 stable isotopes: carbon-12 with 6 protons and 6 neutrons, and carbon-13 with 6 protons and 7 neutrons. In our solar system, the ratio is remarkably consistent, about 89 carbon-12 atoms for every 1 carbon-13 atom. On January 3rd, 2026, the Gemini North Telescope completes a deep spectroscopic observation of 3I Atlas using its high-resolution spectrograph. The object is now 500 million kilometers from Earth, faint and receding, but still detectable with long exposure times. The team is specifically targeting carbon monoxide emission lines in the infrared, looking for subtle wavelength shifts between the different isotopic variants of the molecule. Carbon monoxide made with carbon-12 emits at slightly different wavelengths than carbon monoxide made with carbon-13. The difference is tiny, measured in fractions of a nanometer, but modern spectrographs can resolve it. By comparing the strength of these emission lines, you can determine the carbon-12 to carbon-13 ratio in the gas being released from the comet. The result is unexpected. 3I Atlas shows a ratio of 98.7 to 1, far more carbon-12 relative to carbon-13 than solar system objects show. This isn't a subtle difference or a marginal detection. The signal is clear, measured with high confidence across multiple emission lines that all agree. What does this mean? Carbon-13 forms preferentially in massive stars through the CNO cycle, a fusion process that's more efficient in stars heavier than our Sun. Lower mass stars produce relatively less carbon-13. If 3I Atlas formed in a system around a star less massive than our Sun, perhaps a K-type orange dwarf or an M-type red dwarf, the isotopic ratio would naturally be skewed toward carbon-12. This confirms the object's interstellar origin beyond any remaining doubt, though that was already established from the orbital mechanics. But it also tells us something about where it came from. The isotopic signature points toward formation around a star smaller and cooler than our Sun, likely in a system where planetary formation happened under different chemical conditions than we experienced. However, there's an alternative explanation that nobody wants to write explicitly in their papers, but everyone is thinking about. Isotopic ratios can be modified through industrial processing. If you're extracting and purifying carbon dioxide for storage or propulsion, isotopic fractionation occurs naturally during phase changes and chemical reactions. Different isotopes have slightly different masses, so they behave slightly differently during evaporation, condensation, and molecular assembly. The specific ratio of 98.7 to 1 isn't just random. It falls close to what you'd expect from repeated distillation of carbon dioxide, a process that preferentially concentrates the lighter isotope. Multiple cycles of freezing and thawing, capturing vapor and discarding residue, would drive the ratio progressively higher. Natural formation in an unusual stellar environment, or artificial processing and storage. Both can produce the observed isotopic signature. The data alone cannot distinguish between them, but combined with everything else, the periodic flash, the stable rotation, the sudden activity onset, the composition paradox adds one more piece to a puzzle that's looking less like a comet and more like something else entirely. Every object in space reaches thermal equilibrium with its environment. Solar radiation heats the surface. The surface radiates that heat back into space as infrared. And eventually, the temperature stabilizes at a point where incoming energy equals outgoing energy. This isn't complicated physics. It's the same reason why a black car parked in the sun gets hotter than a white car. Surface properties and solar distance determine the equilibrium temperature with predictable precision. For 3I Atlas, at its current distance from the Sun, approximately 520 million kilometers as of early January 2026, the expected surface temperature is around 130 Kelvin, which is negative 143 degrees Celsius. That calculation assumes a surface with typical cometary properties, low reflectivity, around 4 to 6%, and efficient thermal radiation in the infrared. The coma complicates things slightly by providing some shading and absorbing some sunlight before it reaches the nucleus, but the effect is minor. Infrared observations tell a different story. The Spitzer Space Telescope was retired in 2020, but its archive contains an enormous catalogue of infrared sky surveys. A data mining project in late December 2025 discovers that Spitzer happened to image the region where 3I Atlas is currently located back in 2018 during one of its final survey campaigns. The object wasn't there at that time, obviously, but the archival data provides a baseline measurement of the infrared background in that part of the sky. Current infrared observations from ground-based telescopes, including the NASA Infrared Telescope Facility in Hawaii, show 3I Atlas against that same background. By comparing the object's thermal emission to the known background, you can extract its temperature with reasonable accuracy. The measurement comes back at 115 Kelvin, 15 degrees cooler than the equilibrium calculation predicts. 15 Kelvin might not sound like much, but in thermal physics, every degree matters. At these temperatures, radiation follows the Stefan Boltzmann law, where emitted power scales with the fourth power of temperature. Being 15 degrees cooler means the object is radiating significantly less energy than it receives from the Sun. That energy imbalance has to go somewhere. There are limited natural explanations. First possibility: the surface is more reflective than assumed. If 3i Atlas reflects 30 or 40% of incoming sunlight instead of 4 to 6%, it would absorb less energy and reach a lower equilibrium temperature. But optical observations constrain the albedo. Outside of those brief 0.7-second flashes, the object appears dark. High reflectivity contradicts the photometry. Second possibility: the outgassing provides evaporative cooling. When ice sublimates, it absorbs energy from the surface, cooling it below the radiative equilibrium temperature. This happens with comets, but the magnitude of cooling depends on the sublimation rate. For 15 degrees of cooling, you'd need vigorous outgassing, much stronger than what's observed. The coma brightness and gas production rates aren't high enough to account for the temperature deficit. Third possibility: something is actively removing heat. Internal systems generating power, then radiating that heat in a controlled manner, could maintain surface temperatures below equilibrium. Spacecraft do this routinely with radiators and heat pipes. Natural objects do not. The 15 Kelvin discrepancy is small enough that most researchers don't emphasize it in their papers. It falls within the range of modeling uncertainties and assumptions about surface properties. But it's there, consistently measured across multiple observation epochs. 3i Atlas is cooler than it should be, and natural explanations require increasingly specific conditions to make the numbers work. If 3i Atlas is a fragment from a catastrophic disruption event, a planetary collision or tidal breakup that shattered a larger body millions of years ago, then basic physics demands there should be other fragments. Destructive events don't produce single isolated pieces. They create debris fields, streams of material ranging from dust to kilometer-sized chunks, all moving on similar trajectories through space because they share a common origin. The search for companion objects begins in earnest in early January 2026. Multiple survey teams coordinate observations covering a wide region of sky around 3i Atlas's trajectory, looking for anything else moving at similar velocity and direction. The Catalina Sky Survey in Arizona, the Pan-STARRS telescopes in Hawaii, and the European Space Agency's optical ground station in Tenerife all contribute observation time. The search parameters are generous. Companion fragments might have been ejected at slightly different velocities during the original disruption event, so their current positions could be spread across millions of kilometers. They might be smaller and fainter than 3i Atlas itself, requiring deep exposures to detect. They might have different activity levels, some outgassing vigorously, others completely inert. The surveys are designed to catch anything down to magnitude 24, which would reveal objects as small as 50 meters across, if they're reflective enough. After 3 weeks of intensive searching, covering a volume of space encompassing 10 million cubic kilometers around the predicted trajectory, the surveys find nothing. No companions, no smaller fragments, no debris trail of dust particles that would mark the path of a disrupted body slowly shedding material. The space around 3i Atlas is empty. This absence is statistically significant. Models of catastrophic disruption predict size-frequency distributions following power laws. For every large fragment, there should be dozens of medium-sized pieces and thousands of small ones. If 3I Atlas is a 5-kilometer fragment, there should be at least 10 fragments in the 1 to 2 kilometer range within the search volume. The probability of detecting 0 companions when 10 or more should exist is less than 1%. The searches extend to dust detection. The Infrared Astronomical Satellite and the Wide Field Infrared Survey Explorer have both mapped infrared background emission across the sky. Dust trails from disrupted objects show up as faint streaks of thermal emission, warmed by sunlight and radiating in the infrared. Analysis of archival data covering 3I Atlas's trajectory back to 2010 reveals no excess infrared emission, no dust trail, no diffuse debris cloud. There's also no evidence of mass loss beyond the active outgassing. Long exposure images from professional observatories would reveal fragments or particles being shed from the nucleus, creating a debris trail behind the object as it moves. Such trails are common for active comets and have been observed in solar system examples. 3I Atlas shows no such feature. The coma exists, the gas and dust being actively released, but there's no trail of solid debris marking its path. 3I Atlas travels alone. If this is a fragment from a disrupted world, either it's the only survivor of an event that somehow produced just one large piece, or the companions exist but are too small, too dark, and too dispersed for current surveys to detect. Both scenarios are possible, but neither is likely. The simplest explanation for finding no companions is that there are no companions because 3I Atlas isn't a fragment at all. The lobe scale was designed to be provisional, a framework for quantifying uncertainty rather than declaring certainty. When Avi Loeb first proposed rating interstellar objects on a 0 to 10 scale of artifact probability, the astronomical community responded with skepticism, ranging from polite to hostile. Quantifying the likelihood of extraterrestrial technology seemed premature at best, attention-seeking at worst. But frameworks exist to be tested, and 3I Atlas is providing that test. In mid-January 2026, 3 independent research groups publish assessments using Loeb's methodology. The first group from Caltech approaches it purely from anomaly accumulation. They list every observation that deviates from natural comet behavior: the periodic brightness flash, the stable rotation, the decreasing activity at perihelion, the unusual isotopic ratios, the thermal deficit, the absence of companions, the sudden onset of outgassing. Each anomaly individually has possible natural explanations, but the probability of all of them occurring together in a single object is vanishingly small. Their calculation arrives at 7.2 out of 10. Not because they believe 3I Atlas is definitely artificial, but because natural explanations require increasingly contrived combinations of unlikely circumstances. The artifact hypothesis, while extraordinary, is becoming statistically competitive with the natural hypothesis when you account for all observations simultaneously. The second group from the European Southern Observatory focuses on falsification. They ask what observations would be required to definitively rule out the artifact hypothesis, and they find that most conceivable observations wouldn't be sufficient. Seeing typical comet behavior would help, but 3I Atlas isn't showing typical behavior. Detecting natural molecules in the coma was supposed to argue for natural origin, but those detections are already confirmed and haven't resolved the anomalies. Their assessment reaches 6.8 out of 10, acknowledging that the hypothesis has become difficult to falsify with available data. The third group, an international collaboration including researchers from Japan, Australia, and Chile, takes the most conservative approach. They weight natural explanations more heavily, giving significant credit to the confirmed presence of water and carbon dioxide, and the lack of any detected maneuvers or radio signals. Their rating is 5.5 out of 10, barely above the midpoint, but still elevated compared to where any assessment stood 3 months ago. 3 independent teams, 3 slightly different methodologies, all converging on scores between 5.5 and 7.2. The average lands at 6.5. Loeb's original early assessment of 6 out of 10, later revised down to 4, turns out to have been closer to correct than the mainstream dismissal at near 0. The anomalies were real, the questions were legitimate, and the object remains genuinely unexplained. The United Nations Committee on the Peaceful Uses of Outer Space was established in 1959 to govern international cooperation in space exploration and prevent the militarization of orbit. For 67 years, COPUOS has dealt with satellite regulations, debris mitigation, and coordination of space activities among member nations. On February 1st, 2026, it convenes an emergency session to address something entirely outside its historical mandate: what to do about 3I Atlas. 37 nations send representatives to Vienna for the closed session. The meeting agenda, later published in summary form, reveals the scope of disagreement. Should humanity attempt communication with the object? Who has the authority to make that decision? What are the legal implications if 3I Atlas is determined to be artificial? Does the Outer Space Treaty, which governs celestial bodies and prohibits national appropriation, even apply to objects from other star systems? The debates reportedly become heated immediately. Several nations argue for immediate active messaging, transmitting radio signals toward 3I Atlas to test for response. The technical capability exists through facilities like the Deep Space Network and various radio telescopes worldwide. A simple mathematical sequence, prime numbers or basic arithmetic, could demonstrate intelligence without conveying complex information. If the object is a probe, and if it's still functional, it might respond. Other delegations vehemently oppose any transmission. They invoke dark forest arguments. Broadcasting our presence to an unknown entity of uncertain origin and capability is reckless. We don't know who built it, when it was built, or what its purpose might be. Drawing attention could invite catastrophic consequences. Better to observe silently and learn what we can without revealing ourselves. A third faction argues the debate is premature. 3I Atlas has shown no signs of active communication, no attempts to alter trajectory toward Earth or any planet, and no responses to ambient radio noise from our civilization. Assuming it's listening or capable of responding requires assumptions not supported by evidence. Any transmission would likely go unanswered, wasting resources and political capital, while accomplishing nothing except generating more public anxiety. The session concludes without resolution. COPUOS establishes a working group to draft guidelines for responding to interstellar objects of undetermined origin, but no immediate action is authorized. The committee's published statement emphasizes continued observation, international data sharing, and the need for coordinated scientific assessment before any active measures are considered. Behind the diplomatic language, the fundamental disagreement remains: wave or stay silent, and humanity as fractured and argumentative as ever, cannot agree which approach protects us better. The object continues outward, indifferent to our debates, while the clock runs down on our window to do anything at all. The SETI community has spent decades listening for signals from space, but transmission, deliberately broadcasting messages toward other potential civilizations, remains deeply controversial. The technical term is METI, messaging to extraterrestrial intelligence, and it divides researchers into camps that rarely find common ground. 3i Atlas brings this philosophical debate into immediate practical focus. On February 7th, 2026, a coalition of research institutions, including the SETI Institute, Breakthrough Listen, and several university astronomy departments, announces plans for an active transmission attempt. The proposal is straightforward. Use the Goldstone Deep Space Communications complex to broadcast a repeating mathematical sequence toward 3i Atlas's projected position for 72 continuous hours starting February 15th. The message would consist of prime numbers, basic arithmetic operations, and simple geometric ratios, concepts that any technological civilization should recognize. The transmission would be powerful enough to be detectable by receiving equipment comparable to our own across the current distance to 3i Atlas, now roughly 600 million kilometers and increasing. If the object contains functional receivers and processing systems, if it's still operational after however long it's been traveling through interstellar space, if it's programmed or designed to recognize and respond to contact attempts, then this transmission represents our best chance for confirmation before the object exits the solar system permanently. The opposing response arrives within hours. An open letter signed by 83 scientists, including several prominent astronomers and astrobiologists, condemns the transmission plan as reckless and irresponsible. Their argument centers on uncertainty and asymmetric risk. We don't know what 3i Atlas is, where it came from, or what its capabilities might be. Broadcasting our technological presence, demonstrating that Earth harbors intelligent life capable of radio communication, could draw unwanted attention. The letter invokes the dark forest hypothesis directly. If the galaxy contains civilizations advanced enough to send probes across interstellar distances, and if those civilizations view other intelligent species as potential threats or competitors for resources, then announcing our presence is existentially dangerous. We're lighting a fire in a forest where we don't know if the other inhabitants are friendly, hostile, or simply pragmatically eliminationist. The counter-argument from the transmission advocates is that remaining silent accomplishes nothing. 3i Atlas, if artificial, has already passed through the inner solar system. It has certainly detected our planet, observed our atmospheric composition, potentially indicating biological activity, and quite possibly noticed our radio and radar emissions leaking into space. Silence at this point isn't stealth, it's just missed opportunity. If we're already visible, we might as well attempt communication. The debate goes public. Social media erupts with hashtags supporting both sides. Polls show humanity split roughly 50-50 on whether to transmit. The Goldstone transmission window approaches, and no international authority has the power to stop a participating institution from using its own equipment. The question isn't whether we should signal, it's whether anyone can or will. By mid-February 2026, the scientific uncertainty about 3i Atlas has metastasized into full-blown cultural division. The object has transcended astronomy and become a Rorschach test where people see reflections of their existing worldviews, fears, and hopes. Social media platforms, already strained by years of misinformation and tribal politics, fracture along new fault lines. The Hello Atlas movement emerges first, advocating for immediate transmission and open communication. Their argument is optimistic. If we've been found by an interstellar probe, that's extraordinary and wonderful. It means we're not alone. It means someone out there achieved interstellar travel and chose to explore rather than destroy. Meeting that achievement with silence is cowardice. Thousands of users change their profile images to variations of radio wave symbols and write messages they hope will somehow reach the object. The opposing dark forest real community grows just as quickly. They view any transmission as civilizational suicide, a naive invitation to predators we can't comprehend or defend against. Their posts catalogue historical examples of technologically advanced civilizations encountering less advanced ones, outcomes that rarely favoured the less powerful. They argue that cosmic silence is the norm precisely because survival requires stealth, and breaking that silence for curiosity is gambling with every human life. Between these poles, conspiracy theories multiply. Some claim governments have known about 3I Atlas since it entered the solar system and have been secretly communicating with it for months. Others insist the entire story is fabricated, that no such object exists, and the narrative is being used to justify increased surveillance or military spending. Still, others propose that 3I Atlas is human-made, a classified military project being disguised as an interstellar visitor. The scientific community finds itself under siege from all directions. Researchers who emphasize uncertainty and call for more data are accused of cover-ups by believers and of giving credence to nonsense by skeptics. Those who publicly state the object is likely natural receive harassment from people convinced of alien origins. Those who acknowledge the anomalies and suggest artifact hypotheses deserve consideration, face professional attacks from colleagues who view any such discussion as career-damaging pseudoscience. Several astronomers involved in 3I Atlas research report doxing, threatening emails, and harassment of family members. Online mobs demand answers that science cannot yet provide, and the absence of definitive conclusions is interpreted as evasion rather than honest uncertainty. Trust in institutions, already eroding for years across many societies, takes another hit. When experts say, "We don't know," a significant portion of the public hears, "We won't tell you." The fracture lines run deep, dividing not just online communities, but families, friendships, and professional relationships. And through it all, 600 million kilometers away and receding, 3I Atlas continues its journey, utterly indifferent to the chaos it's created simply by existing. The sales data tells a story that mainstream media largely ignores. Starting in late January 2026 and accelerating through February, emergency preparedness suppliers report unusual demand patterns. Not panic buying, not the frenzied emptying of shelves seen during natural disasters or pandemic scares, but steady, deliberate purchasing of long-term storage food, water filtration systems, backup power supplies, and communications equipment. The increase is global and consistent across demographics. A supplier in Colorado reports sales up 42% compared to the same period in 2025. A company in Germany specializing in off-grid power systems sees orders triple. manufacturers of freeze-dried meals designed for camping and emergency preparedness report back orders stretching weeks into the future. These aren't survivalist extremists stockpiling for imagined apocalypse. These are ordinary families making quiet preparations for an uncertainty they can't articulate but feel compelled to hedge against. Interviews with customers, when they agree to speak, reveal a common thread. They don't necessarily believe 3i Atlas is an alien spacecraft, or that contact is imminent. Most express skepticism about the more sensational interpretations. But they've absorbed the underlying message: we're not alone, or at least we might not be alone, and nobody in authority seems to know what that means or what might happen next. In the face of that fundamental uncertainty, the basic human impulse toward preparedness activates. The psychology is more complex than simple fear. It's about control and agency in a situation where both feel absent. You can't control whether an interstellar object is natural or artificial. You can't influence what governments or scientists decide to do about it. You can't affect the trajectory of something moving at 58 kilometers per second. But you can fill your basement with supplies. You can install solar panels. You can ensure your family has water and food reserves. Preparation becomes a psychological buffer against helplessness. Financial markets show subtler effects. Stocks in aerospace and defense companies tick upward. Cryptocurrency prices fluctuate wildly as some investors view decentralized systems as hedges against institutional uncertainty. Gold purchases increase modestly. None of these movements constitute panic or crash, just widespread, low-level anxiety manifesting in thousands of individual economic decisions. Mental health professionals report increased client visits related to existential anxiety. Not clinical disorders requiring intervention, just people processing the cognitive dissonance of living in a world where the question "are we alone?" might be shifting from philosophical to practical. Therapists describe it as anticipatory stress without clear object, worrying about something that hasn't happened and might not happen, but feels more possible than it did 6 months ago. The preppers aren't building bunkers or forming militias. They're buying batteries and canned goods, taking small concrete actions against vast abstract uncertainty. And whether 3i Atlas is comet or craft, that response might be the most human part of this entire story. The brightness flash, captured by Mars Express in October, becomes the subject of intensive analysis throughout February 2026. Multiple teams apply photometric techniques originally developed for studying asteroid surfaces and spacecraft reflections, attempting to extract every possible detail from those 6 brief events recorded across 14 hours. The reflective surface geometry can be constrained through timing and brightness. Each flash lasts approximately 0.7 seconds, which at the object's rotation period of 4 hours 17 minutes represents about 0.005% of a full rotation. This gives the angular width of the reflective region, roughly 1.8 degrees of arc around the rotation axis. Combined with estimates of the object's size, this constrains the physical dimensions. If 3i Atlas is 5 kilometers in diameter at its widest point, the reflective patch spans approximately 150 meters. If the object is smaller, closer to the 1 kilometer lower, estimates some models suggest the patch is proportionally smaller, around 30 meters. But cross-referencing with the radar observations from Goldstone, which showed unexpectedly high radar return consistent with smooth surfaces, supports the larger size estimate. The most probable dimensions for the reflective region fall between 40 and 80 meters across. The brightness increase during the flash is 8-fold in the infrared channel, corresponding to an albedo reflectivity of approximately 85% during those brief moments. For context, fresh snow reflects about 80 to 90% of visible light. Aluminum foil reflects around 88%. Dirty cometary ice reflects 4 to 6%. Water ice in its cleanest form might reach 30 to 40% reflectivity. 85% albedo requires an exceptionally smooth, clean surface with optical properties, unlike any natural material found on comets. The flash timing provides additional information. It occurs when the reflective surface is oriented within approximately 15 degrees of perpendicular to the sun line, the direction from the object toward the sun. This is exactly what you'd expect for specular reflection, where light bounces off a flat surface like a mirror, rather than scattering diffusely, like it does from rough surfaces. The reflection is directional and geometric, not the broad scattering you see from ice crystals or dust. Analysis of the flash's spectral properties shows it matches solar spectrum almost perfectly. The reflected light has the same color ratios as direct sunlight, confirming this is pure reflection rather than fluorescence or thermal emission. Whatever material comprises this surface is reflecting without significantly absorbing or re-emitting at different wavelengths. The conclusion from multiple independent photometric analyses converges. 3I Atlas contains a region 40 to 80 meters across that is flat to within a few degrees, smooth at centimeter scales based on radar properties, and reflective enough to rival manufactured materials. Natural geological processes don't create and maintain surfaces with these combined properties, especially not surfaces that remain pristine after millions of years traveling through the radiation and micrometeorite environment of interstellar space. The weak non-gravitational acceleration that puzzled researchers since August 2025 takes on new significance when reanalyzed in light of the controlled rotation and sudden activity onset. Initially dismissed as evidence of balanced jets or high mass, the acceleration pattern now reveals details that make natural explanations increasingly strained. Precise astrometry from 5 months of observations allows orbital dynamicists to measure not just the magnitude of acceleration, but its direction and stability over time. The acceleration vector, the direction the object is being pushed, remains remarkably constant relative to the Sun. It points almost exactly away from the solar direction throughout the observation period, varying by less than 5 degrees, despite the object's rotation and changing position in its orbit. This stability is exactly what you'd expect from solar radiation pressure, or symmetrically distributed thermal outgassing, where jets on all sides balance out to produce net thrust in the anti-solar direction. But the magnitude is wrong for radiation pressure alone. An object the size of 3I Atlas, even with the high reflectivity of that 40 to 80 meter patch, would experience negligible radiation pressure, far too small to account for the measured acceleration. The push has to come from mass ejection, from outgassing carrying momentum away from the object. Here's where the efficiency calculation becomes problematic. JWST measured the carbon dioxide and water production rates back in August, approximately 100 kilograms per second of gas being released. You can calculate how much thrust that mass flow should produce, using basic rocket equation physics. The momentum of the ejected gas, its mass times velocity, creates an equal and opposite reaction force on the nucleus. For typical cometary outgassing, gas molecules are ejected at velocities around 0.5 kilometers per second. The speed they acquire from thermal energy as ice sublimates and vapor expands. At 100 kilograms per second outflow rate and 0.5 kilometers per second exhaust velocity, the thrust generated should be about 50 newtons, comparable to the weight of a 5 kilogram mass on Earth. But to produce the observed acceleration on an object with minimum estimated mass of 33 billion kilograms requires thrust around 150 newtons, 3 times higher than the measured outgassing should provide. Either the gas is being ejected much faster than thermal velocities predict, around 0.9 kilometers per second, or there's additional mass loss we're not detecting, or the object is significantly lighter than mass estimates suggest. Faster exhaust velocities require more than just thermal sublimation. You need directed expansion, nozzles or vents, that accelerate the gas beyond what temperature alone provides. Natural cometary vents can achieve some collimation through geometric effects, narrow cracks focusing the flow, but reaching 0.9 kilometers per second. Exhaust velocity is at the extreme end of natural processes and requires very specific conditions. The alternative is that what appears to be comet outgassing is actually something else. A propulsion system venting carbon dioxide as reaction mass would look very similar to natural sublimation in spectroscopy. The chemical signature would be identical, but the efficiency, the thrust per unit mass expelled, could be much higher if the gas is being actively accelerated through designed mechanisms, rather than simply boiling off from solar heating. The specific impulse, a measure of rocket engine efficiency defined as thrust divided by propellant mass flow rate, calculates to around 150 seconds for 3I Atlas if we trust the mass estimates. That's low by spacecraft standards. Chemical rockets achieve 300 to 400 seconds, but it's remarkably high for passive thermal sublimation, which typically produces specific impulses below 50 seconds. We're looking at propulsion efficiency that falls exactly between natural and artificial, uncomfortably efficient for a comet, surprisingly inefficient for designed technology, and right in the gap where neither explanation fits cleanly. Cosmic rays are high-energy particles, mostly protons, that flood through space at nearly the speed of light. They originate from supernovae, active galactic nuclei, and other violent cosmic events, and they bombard every surface exposed to the interstellar environment. When these particles strike atoms in rocks or ice, they trigger nuclear reactions that create distinctive isotopes not normally present in material. These cosmogenic isotopes accumulate over time, creating a clock that records how long a surface has been exposed to space. In late February 2026, a team analyzing the unusual carbon isotope ratios in 3I Atlas's outgassed carbon dioxide realizes they can extract cosmic ray exposure, age, from the same spectroscopic data. The technique is indirect and requires assumptions about initial composition, but certain isotopic signatures are unmistakable markers of radiation damage. The presence of specific noble gas isotopes, particularly helium-3 and neon-21, can only be created through cosmic ray spallation reactions. These isotopes don't form during normal stellar nucleosynthesis or planetary processes. they're purely products of high-energy particle bombardment. The ratios detected in the gas being released from 3I Atlas, when modelled against known cosmic ray flux in the interstellar medium, suggest surface exposure times between 50 and 100 million years. 50 million years is an incomprehensibly long time on human scales. When 3I Atlas began its journey through interstellar space, Earth was in the Eocene epoch. Primates were just beginning to diversify. Grasses had recently evolved. The continents were still drifting toward their current positions. And something, whether through natural ejection or deliberate launch, sent this object on a trajectory that would eventually bring it through our solar system. 100 million years pushes back into the Cretaceous period. Dinosaurs still dominated Earth. Flowering plants were spreading across the continents. No primate, no mammal larger than a small rodent, nothing remotely resembling human intelligence existed. Yet this object was already traveling between the stars. These timescales create profound problems for the artifact hypothesis. Technology that functions after 50 to 100 million years of exposure to cosmic radiation, micrometeorite bombardment, and the extreme cold of interstellar space requires engineering beyond anything humans have achieved or seriously contemplated. Our most durable spacecraft, the Voyager probes, launched in 1977, are expected to cease functioning within decades as their power supplies decay and systems fail. The idea of a functional probe operating after millions of years seems to violate everything we understand about material degradation and system reliability. But the same timescales create problems for natural explanations too. An object ejected from a planetary system 50 million years ago has travelled extraordinary distances. At typical interstellar velocities of 20 to 30 kilometers per second, it would have covered 1,500 to 3,000 light years. Yet, gravitational interactions with passing stars during such a long journey should have significantly altered the trajectory, potentially sending the object in completely different directions multiple times. The probability that an object wandering randomly through the galaxy for 50 million years would happen to pass through our solar system is vanishingly small, unless such objects are extraordinarily common, far more common than current models of planetary system formation suggest. We're back to the statistics problem that's haunted 3I Atlas from the beginning. Finding something this old, this large, and this unusual, as only our third interstellar detection, requires either extraordinary luck or a fundamental misunderstanding of the interstellar object population. The cosmic ray exposure age doesn't resolve whether 3I Atlas is natural or artificial. It just makes both explanations harder to accept. Ancient beyond easy comprehension, the object challenges our assumptions about what's possible, what's probable, and what we should expect to find in the space between stars. Cosmic rays are high-energy particles, mostly protons, that flood through space at nearly the speed of light. They originate from supernovae and active galactic nuclei, bombarding every surface exposed to the interstellar environment. When these particles strike atoms in rocks or ice, they trigger nuclear reactions, creating distinctive isotopes. These cosmogenic isotopes accumulate over time, forming a clock that records how long a surface has been exposed to space. In late February 2026, a team analysing the carbon isotope ratios in 3I Atlas realises they can extract cosmic ray exposure age from spectroscopic data. The technique requires assumptions about initial composition, But certain isotopic signatures unmistakably mark radiation damage. Specific noble gas isotopes, particularly helium-3 and neon-21, form only through cosmic ray spallation reactions. These don't arise during normal stellar processes or planetary formation. They're purely products of high-energy particle bombardment. The ratios detected in outgassed material, modelled against known cosmic ray flux in interstellar medium, suggest surface exposure, times between 50 and 100 million years. 50 million years ago, Earth was in the Eocene epoch. Primates were just diversifying. Grasses had recently evolved. Something, through natural ejection or otherwise, sent this object on its interstellar trajectory. 100 million years pushes into the Cretaceous period, when dinosaurs dominated and no mammal larger than rodents existed. Yet this object was already travelling between stars. These timescales devastate the artifact hypothesis. Technology functioning after 50 to 100 million years of cosmic radiation, micrometeorite impacts, and interstellar cold requires engineering beyond anything humanity has achieved or contemplated. Our most durable spacecraft, Voyager probes launched in 1977, will cease functioning within decades as systems fail. A probe operating after millions of years seems impossible, given material degradation and system reliability limits. But natural explanations face equal problems. An object ejected 50 million years ago has travelled extraordinary distances. At typical interstellar velocities of 20 to 30 kilometers per second, it would cover 1,500 to 3,000 light-years. Gravitational interactions with passing stars during such journeys should significantly alter trajectories, potentially redirecting the object multiple times. The probability that something wandering randomly through the galaxy for 50 million years would pass through our solar system is vanishingly small, unless such objects are extraordinarily common, far more abundant than planetary formation models suggest. The statistics problem returns. Finding something this old, this large, this unusual, as only our third interstellar detection, requires either extraordinary luck or fundamental misunderstanding of the interstellar object population. The cosmic ray exposure age resolves nothing about 3I Atlas's nature. It makes both natural and artificial explanations harder to accept. Ancient beyond comprehension, the object challenges assumptions about what's possible, probable, and what we should expect in the space between stars. Tracing the origin of an interstellar object is extraordinarily difficult. The challenge isn't just distance or time, though both are formidable obstacles. It's that space itself is dynamic. Stars move, orbits shift, gravitational perturbations accumulate, and what seems like a straight line backward through time becomes increasingly uncertain with every million years you calculate. By March 2026, multiple research groups have attempted to reconstruct 3I Atlas's trajectory in reverse, working backward from its current precisely measured orbit to infer where it might have originated. The mathematical approach is straightforward in principle. Take the object's current position and velocity, subtract the gravitational effects of every massive body it passed near, account for the sun's motion through the galaxy, include the effects of galactic rotation, and trace the path back through time. In practice, the uncertainties explode rapidly. Current measurements give us the object's position to within a few hundred kilometers, and velocity to within meters per second. Excellent precision for tracking something moving at 58 kilometers per second. but propagate that backward for 1 million years, and the position, uncertainty, grows to hundreds of light years. Go back 10 million years, and you're talking about thousands of light years of uncertainty. At 50 million years, the cosmic ray exposure age suggested by isotopic analysis, the error cone encompasses a substantial fraction of our local galactic neighborhood. Despite these limitations, probabilistic models can identify regions of space where 3I Atlas more likely originated versus regions it almost certainly did not pass through. A collaboration between astronomers at Leiden Observatory, the Harvard-Smithsonian Center for Astrophysics, and the Space Telescope Science Institute publishes the most comprehensive backtracing analysis in early March. Their model accounts for the gravitational influence of every star within 300 light-years of the Sun, with known proper motion from the Gaia spacecraft's astrometric survey. It includes the effects of giant molecular clouds, whose gravitational fields can slightly deflect passing objects. It factors in the asymmetric potential of the Milky Way's spiral arms, and the vertical oscillation of stars above and below the galactic plane. The computation requires weeks of supercomputer time and produces not a single answer, but a probability distribution across three-dimensional space and time. The results point toward a source region approximately 180 light-years away in the general direction of the constellation Ophiuchus. The uncertainty is enormous, a volume of space roughly 200 light-years across and 100 light-years deep, containing thousands of stars. But it's better than no constraint at all. Somewhere in that volume, something happened 50 to 100 million years ago that sent 3I Atlas on its journey. The team cross-references this source region with stellar catalogues looking for unusual systems, stars that might have experienced catastrophic events, or possess planetary systems likely to produce interstellar ejecta. They find 17 stars within the probability zone that show signs of being older than 5 billion years, similar to our Sun's age. 3 of these stars have detected debris disks, circumstellar material that might indicate active planetary dynamics or past collisions. One star in particular catches attention, a K-type orange dwarf designated HD 147513, located 178 light-years away. Spectroscopic measurements show this star has slightly lower metallicity than our Sun, meaning fewer heavy elements in its composition. Planets forming around such stars would have different chemical abundances, potentially explaining the unusual isotopic ratios seen in 3I Atlas's outcast material. The star's age is estimated at 6 billion years, old enough to have formed a mature planetary system that might have undergone late-stage gravitational instabilities. HD 147513 has no confirmed planets detected yet, though that's unsurprising, given the limits of current exoplanet detection methods for stars at that distance. But absence of detection doesn't mean absence of planets. Most planetary systems remain undetected simply because we haven't looked carefully enough, or because the geometry doesn't favor detection from Earth's vantage point. The inference is tantalizing, but ultimately inconclusive. 3I Atlas might have originated from the region around HD 147513, or from any of thousands of other stars in that probability volume, or from somewhere else entirely, if the trajectory reconstruction contains systematic errors we haven't identified. The uncertainty is honest and unavoidable. What the analysis establishes is that 3I Atlas has been travelling for an immensely long time across extraordinary distances. Whether launched deliberately or ejected naturally, whether functional technology or inert debris, it's a messenger from a place and time far removed from anything humanity has direct knowledge of. And whatever happened there, in that distant star system, dozens of millions of years ago, we're only now receiving the evidence. December 4th, 2025, while the astronomical community was still processing the Mars Express brightness anomalies, a completely separate discovery emerged from an entirely different dataset. A graduate student mining archival observations from the Transiting Exoplanet Survey satellite noticed something peculiar in data captured 6 years earlier. TESS launched in 2018 with a singular mission: find planets around other stars by detecting the tiny brightness dips when those planets pass in front of their host stars. The spacecraft photographs vast swaths of sky continuously, measuring the brightness of hundreds of thousands of stars simultaneously, looking for the periodic dimming that reveals orbiting worlds. Star Tick 4 7748 3291, an unremarkable G-type star similar to our Sun, located 178 light-years away in the constellation of Fucus, showed exactly such a dimming event in test data from August 2019. But the transit pattern was wrong. Normal planetary transits are periodic. The planet orbits its star on a closed ellipse, passing in front predictably with clockwork regularity. Earth transits the Sun every 365 days, as seen from distant vantage points. Jupiter transits every 12 years. The periodicity is the signature of gravitational binding. This transit wasn't periodic. It appeared once in the test data across 2 years of observations covering that star. A single dimming event lasting approximately 18 hours, reducing the star's brightness by 0.03%, then nothing. No repeat. No second transit. The shape of the light curve also didn't match planetary expectations. Planetary transits produce smooth, U-shaped dips as the circular planet disk gradually covers and then uncovers the stellar surface. This event showed irregularities, small fluctuations in the dimming profile, suggesting the transiting object wasn't spherical. Most troubling was the velocity. By measuring the duration of the transit and the amount of dimming, you can calculate how fast the object moved across the stellar disk. This object crossed far too quickly for a gravitationally bound orbit at that distance from the star. The implied velocity was consistent with hyperbolic trajectory, something passing through the system rather than orbiting within it. TIC 4774833291 is HD 147513, the same star identified as the probable source region for 3I Atlas, based on trajectory reconstruction. 178 light-years away, same distance, same direction, and 6 years ago, something passed in front of it, moving too fast to be captured by that star's gravity. Let's construct the strongest possible case for 3I Atlas being a natural object, because intellectual honesty requires steel manning the opposition. Dismissing alternatives without rigorous examination is how science fails. And the natural comet hypothesis, while strained, isn't definitively ruled out by current observations. Start with what we know is unambiguously natural: the chemical composition. JWST detected water, carbon dioxide, carbon monoxide, and carbonyl sulfide, all standard cometary volatiles. No exotic compounds, no industrial chemicals, no molecular signatures that scream artificial synthesis. the coma exists and behaves like sublimating ice, releasing gas and dust. That's fundamentally comet behavior. The unusual 8:1 carbon dioxide to water ratio, while rare in our solar system, could absolutely result from formation in a different stellar environment. Protoplanetary disks around lower mass stars, or in regions with different chemical abundances, would produce comets with compositions we don't see locally. Finding one unusual comet from another star system doesn't mean artificial. It means our sample of one local population gave us false expectations about galactic diversity. The stable rotation at 4 hours 17 minutes might be coincidence or selection bias. We've only observed 3 interstellar objects. Maybe stable rotators are more common than chaotic tumblers in the interstellar population, because something about the ejection process or long-term evolution favors rotational stabilization. We don't have enough data to know what's typical. The brightness flash could be exotic ice physics we haven't seen because we've never studied comets that spent millions of years in deep space at near absolute zero temperatures. Radiation processing, phase transitions in crystalline structures, or surface phenomena unique to interstellar environments might produce reflective patches that natural but unprecedented. The sudden activity onset between June and July could be triggered by internal heating from radioactive decay, finally reaching critical subsurface layers, or structural failure in radiation, damaged crust, allowing trapped volatiles to escape suddenly. Comets can exhibit threshold behavior where activity switches on abruptly rather than gradually. The absence of companion objects might just mean they're too small or too dispersed for current surveys to detect. The statistics of finding large objects first could be explained by detection bias we haven't fully characterized. Every individual anomaly has at least one possible natural explanation. The problem remains that requiring all of them simultaneously stretches probability thin. But improbable isn't impossible, and the universe has surprised us before with natural phenomena that seemed impossible until we understood them better. If 3I Atlas is artificial, what does that actually mean? The implications branch into multiple scenarios, each with profoundly different consequences for how we understand our place in the cosmos and what might happen next. Scenario 1. Functional probe. 3I Atlas is an active reconnaissance spacecraft, still operational after 50 million years of interstellar travel, designed to observe planetary systems as it passes through. The brightness flash might be a solar panel or antenna catching sunlight. The controlled rotation maintains pointing stability for instruments. The outgassing could be intentional venting for thermal management or minor course corrections. In this scenario, something is watching us right now, collecting data about Earth, our atmosphere, our electromagnetic emissions, and presumably detecting signs of technological civilization. If it's functional, does it report back? Has it already transmitted findings to whoever launched it millions of years ago? At the speed of light, a radio signal from our solar system would take 178 years to reach HD 147513. If the probe transmitted when it entered the system in early 2025, the message arrives in 2203. If the origin civilization still exists and responds immediately, we'd receive their reply around 2481. This is multi-generational communication at minimum. Scenario 2. Derelict technology. 3I Atlas was functional once, but has been dormant for millions of years. Systems have failed, power has depleted, whatever intelligence guided it is long gone. We're seeing residual structure, the physical remnants of engineering that was never designed to last this long, but happened to survive through robust construction or favourable luck. The rotation continues through momentum. The reflective surface is a dead solar panel or structural component. The outgassing might be stored propellant slowly leaking through degraded seals. In this scenario, we're looking at an archaeological artifact, a fossil of someone else's space age. Scenario 3, fragment of something larger. 3I Atlas isn't a complete spacecraft, but a piece of one. Perhaps a probe was destroyed by collision with interstellar debris or internal malfunction. And this is the surviving section. The anomalies we see reflect partial systems still minimally functional or structural elements never meant to be examined in isolation. This scenario means something was out there but isn't anymore. Each possibility demands different responses. A functional probe monitoring us raises questions about intent and capability. A derelict offers scientific value without immediate concern. A fragment suggests other pieces might exist, possibly on trajectories we haven't detected yet. The hardest question remains: if it's artificial, is it unique or common? Are interstellar probes so numerous that finding one as our third detection is merely statistics catching up? Or is 3I Atlas a singular event, an encounter unlikely to repeat in human lifetimes? The Fermi paradox asks a deceptively simple question. If intelligent life is common in the universe, where is everybody? The galaxy is billions of years old, containing hundreds of billions of stars, many with planets in habitable zones. Even if intelligent civilizations arise rarely, and most don't develop interstellar capabilities, statistical arguments suggest we should see evidence of others. Yet, we detect nothing. No megastructures, no obvious engineering projects, no radio signals that unambiguously indicate technology. The silence is profound and troubling. 3I Atlas reframes this paradox in an uncomfortable direction. What if they're not absent? What if they're here, passing through constantly, but designed to be nearly indistinguishable from natural objects? What if the strategy for exploring the galaxy isn't broadcasting presence or building conspicuous structures, but sending quiet probes that observe without revealing themselves? Consider the economics of interstellar exploration from the perspective of a civilization that survived long enough to develop the capability. You can't send crewed missions across light years. The distances are too vast, the energies required too enormous, the timescales too long. But you can send probes, small automated spacecraft designed to coast through interstellar space for millions of years, enter star systems, gather data, and either transmit back or store information for later retrieval. If you're sending probes, how do you design them? Probably not with flashing lights and radio beacons announcing alien technology here. That draws attention, potentially hostile attention, if other civilizations share your caution. Better to make them look natural, like asteroids or comets, objects that won't trigger alarm or curiosity. Design them to use passive observation, watching electromagnetic emissions and atmospheric spectra without active scanning. Make them durable enough to survive millions of years because you can't maintain or retrieve them once launched. This strategy suggests the galaxy might be full of such probes, thousands or millions of them, drifting between stars, occasionally passing through systems like ours. Most would be completely inert, undetectable, except through precise astrometry showing hyperbolic trajectories. A few might still be functional, and statistically, we'd expect to encounter them rarely enough that confirming their artificial nature is difficult, common enough that we've already seen several if we only knew how to recognize them. If this reframing is correct, Oumuamua, Borisov, and 3I Atlas might not be the complete list of interstellar visitors. They might just be the ones we noticed, the ones whose anomalies were strong enough to generate investigation. How many others passed through undetected, catalogued as distant asteroids, or ignored entirely because they didn't do anything obviously strange? The Vera Rubin Observatory will begin answering this question soon. If interstellar objects are common, one per year or more, and if a significant fraction show anomalies like stable rotation, unusual chemistry, or brightness variations that don't fit natural models, then the probe hypothesis moves from speculation to serious consideration. If most look boringly natural, comets and asteroids from other systems ejected through mundane gravitational processes, then 3I Atlas remains an outlier, possibly unique. The Fermi paradox might not be about absence. It might be about camouflage. And we might be living in a galaxy far more watched, far more visited than the silence suggested. We just weren't looking for the right signatures, weren't asking the right questions, until something like 3I Atlas forced us to reconsider what natural actually means. 3I Atlas is now beyond the orbit of Jupiter, approximately 700 million kilometers from Earth, and receding at 40 kilometers per second relative to our planet. In another year, it will cross the orbit of Saturn. In 5 years, Uranus. In 15 years, Neptune. By 2050, it will be farther from the Sun than Pluto ever gets, entering the realm of scattered disk objects and beginning its true departure from our solar system. Tracking will continue as long as the object remains detectable. Ground-based telescopes can follow it for perhaps another 2 to 3 years before it fades below magnitude 25 and becomes too dim for all but the largest observatories with dedicated observation time. Space telescopes, particularly James Webb, and eventually the Nancy Grace Roman Space Telescope, launching in 2027, might maintain detection somewhat longer, but even their capabilities have limits. By 2030, 3I Atlas will likely be untrackable with current technology. We'll know its trajectory well enough to predict its position for centuries, but actually seeing it, measuring whether it's still outgassing or whether any new anomalies appear, that window is closing. Every observation from now until detection becomes impossible is therefore critical. We're gathering the last data we'll ever have on this object, unless future civilizations develop the capability to chase it down. Several proposals for extended observation campaigns are in development. NASA's Deep Space Network, primarily used for communicating with distant spacecraft, has time allocated through 2028 to periodically ping 3I Atlas with radar and listen for returns. The detection in December 2025 proved radar observation is barely possible, and continued attempts might reveal changes in the radar cross-section that would indicate structural evolution or surface activity. Radio telescopes, including the Very Large Array in New Mexico and the Meerkat Array in South Africa, have committed to monitoring for any radio emissions through at least 2030. The probability of detecting artificial signals is considered low, But the scientific value of a positive detection is so high that the investment is justified. Even null results help constrain models and establish that whatever 3I Atlas is, it's not actively broadcasting at detectable power levels. The SETI community remains divided on active transmission. The proposed Goldstone message, scheduled for February 15th, 2026, ultimately proceeded despite objections. For 72 hours, the antenna broadcast a repeating mathematical sequence toward 3I Atlas's predicted position. The transmission reached the object approximately 55 minutes after broadcast, accounting for light travel time across the distance. No response has been detected as of March 2026, nor was one necessarily expected. If 3I Atlas is artificial but dormant, it wouldn't respond. If it's artificial but programmed not to acknowledge contact, it wouldn't respond. If it's natural, obviously it wouldn't respond. The absence of response tells us nothing, except that whatever this object is, it's not configured or programmed to reply to simple, mathematical messages with immediate radio acknowledgement. Future interstellar object detection will be revolutionized by Vera Rubin Observatory, expected to reach full operational capacity in late 2026. The telescope will survey the entire visible sky every few nights, detecting moving objects far fainter than current surveys can reach. Predictions suggest detection rates of 1 to 5 interstellar objects per year once Rubin is fully operational. This flood of new data will answer critical questions. Is 3I Atlas typical or unusual? Do most interstellar objects show anomalies, or is it an outlier? Will we detect velocity clustering suggesting debris streams, or will every object appear independent? The next 5 years of Rubin observations will either normalize 3I Atlas by showing that weird chemistry and stable rotation are common, or they'll make it even more mysterious by showing that most interstellar visitors behave exactly as natural comet models predict. International protocols are being drafted for responding to future detections. The UN Working Group, established in February, expects to publish preliminary guidelines by late 2026, addressing data sharing, observation coordination, and decision frameworks for whether and how to attempt communication. The guidelines won't be binding. No international body has enforcement authority over independent observatories or space agencies, but they'll provide a template for coordination that's currently absent. Planetary defense networks are expanding tracking capabilities specifically for hyperbolic trajectory objects. While 3I Atlas posed no impact threat, the possibility of future interstellar visitors on more dangerous trajectories can't be dismissed. Detection, characterization, and if necessary, deflection of fast-moving interstellar objects presents challenges beyond current asteroid defense capabilities. Research into intercept missions and kinetic deflection strategies for objects moving at 50+ kilometers per second is beginning, though practical implementation is likely decades away. Educational initiatives are spreading through universities and research institutions. A generation of students is entering astronomy and planetary science specifically because of 3I Atlas and the questions it raised. Graduate programs in astrobiology, planetary defense, and interstellar object studies are seeing increased applications. The object has changed not just what we know, but what we want to find out, redirecting human curiosity toward questions that seemed purely theoretical just 2 years ago. 3I Atlas is leaving, but its effects will persist for generations, January 8th, 2026. The Vera Rubin Observatory in Chile completes its first full month of survey operations after years of construction delays and calibration. The 8.4-meter mirror and 3.2 gigapixel camera represent the most powerful sky survey instrument ever built, designed to photograph the entire visible southern sky every few nights and detect anything that moves, changes, or appears where nothing existed before. The automated detection pipeline processes images in near real time, comparing each night's observations to previous nights, flagging objects that have moved relative to background stars. On January 8th at 03:47 Universal Time, the system flags an object designated LSST ISO CO₂-to-water based on its apparent motion across 3 consecutive images spanning 90 minutes. Initial parameters are immediately unusual. The object moves at 2.7 arc-seconds per hour against the stellar background, significantly faster than main belt asteroids, but slower than near-Earth objects. Brightness is magnitude 22.1, faint but well within Rubin's detection threshold. The motion vector doesn't match any known asteroid or comet orbit in the Minor Planet Center database. Within 6 hours, follow-up observations from 3 Southern Hemisphere telescopes confirm the detection and refine the trajectory. The orbital solution converges quickly with high confidence. Eccentricity 1.4, unambiguously hyperbolic. This is interstellar. The 4th confirmed visitor, but LSST ISO 001 is different from its predecessors in critical ways. First, there's no coma. High-resolution imaging from the Gemini South Telescope shows a point source, stellar in appearance, with no extended glow of gas or dust. The object is completely inert at its current distance of 3 astronomical units from the Sun, well within the range where water ice should be sublimating if it were a typical comet. Second, the approach geometry is wrong. Oumuamua, Borisov, and 3I Atlas all entered the solar system at moderate inclinations relative to the ecliptic plane, the flattened disk where most planets orbit. LSST ISO 001 is coming in nearly perpendicular, descending from galactic north at an inclination of 87 degrees. This trajectory maximizes time spent in the inner solar system, passing near multiple planets rather than cutting through quickly. Third, the velocity is lower. Hyperbolic excess velocity, the speed relative to the Sun after accounting for gravitational acceleration, is only 12 kilometers per second compared to 30 to 50 kilometers per second for previous interstellar objects. This thing is moving slowly by interstellar standards, barely fast enough to escape the solar system after its closest approach. Spectroscopic observations begin immediately. Multiple observatories coordinate to capture reflected sunlight from the object across ultraviolet, visible, and infrared wavelengths. The spectrum shows absorption features consistent with silicate minerals, similar to S-type asteroids in our solar system. No volatiles detected, no organic compounds, just rock. The size estimate from brightness and assumed albedo suggests an object between 100 and 300 meters across, smaller than 3I Atlas, but larger than Oumuamua's estimated dimensions. Rotation period is measurable within 72 hours of discovery, 2 hours 41 minutes. The light curve shows minimal variation, suggesting either a nearly spherical shape or rotation pole pointed close to Earth's direction. Initial trajectory calculations predict closest approach to the Sun at 0.9 astronomical units on March 23rd, 2026, just inside Earth's orbit. The object will pass within 40 million kilometers of Earth on April 2nd. Not close by asteroid standards, but near enough for radar observation and detailed spectroscopy. News of the detection spreads through astronomical channels within hours and reaches mainstream media by January 9th. The public response is immediate and intense. Social media explodes with speculation, hope, fear, and demands for answers that nobody has yet. Is this one natural? Is it related to 3I Atlas? Are we seeing a pattern or just random arrivals? The scientific community mobilizes with unprecedented coordination. The protocols drafted over the past months activate smoothly. Data sharing happens through the newly established Interstellar Object Coordination Center. Observation time is allocated across dozens of telescopes worldwide. Communication protocols are reviewed and updated. Everyone remembers the confusion and information chaos that surrounded 3I Atlas. This time, the response is organized. NASA schedules a press conference for January 12th to present initial findings and address public questions. The European Space Agency, the Japan Aerospace Exploration Agency, and representatives from major observatories worldwide will participate. The message will emphasize what's known, what's uncertain, and what observations are planned. 6 weeks until closest approach. 6 weeks to gather more data than we collected on any previous interstellar visitor. 6 weeks to determine if LSST ISO ZOR-1 is just another rock from the cosmos or something more. The detection system worked exactly as designed. Rubin found an interstellar object within its first month of operation. We were ready. This time, we'll know.